So topic 11 is going to be the pigeonhole principle. The basis behind the pigeonhole principle is pretty simple. The idea is that if you have some number of pigeons or boxes or places to which you're going to distribute items, if you have more items to distribute than the number of boxes or places that you have into which you're going to distribute them, then there has to be more than one item in a box or a place. So for example, in these pictures we have pigeons being distributed into 9 cubbies. So here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pigeons. So if you have 10 pigeons and only 9 cubbies or boxes, then there has to be at least one box that contains more than one pigeon. Notice what the pigeonhole principle doesn't say. It doesn't say that there has to be a pigeon in every box. There doesn't. There might be more than one box that contains more than one pigeon. So we could have any number of boxes, for example, that are empty, and we can have more than 2 pigeons in a box. So the pigeonhole principle doesn't tell you how the pigeons or objects are distributed into the boxes. It just tells you if you have more items, then there are places into which you're going to distribute those items. Then there has to be at least one spot that contains more than one item in it. So the pigeonhole principle, if we think about it abstractly and write up a nice definition for it, we say, hey, suppose we have k plus 1 objects, and we're going to distribute those k plus 1 objects into k boxes. Then there has to be at least one box, at least one, that contains 2 or more of the objects. So for example, we could say, how many people do there have to be in a room practicing bad social distancing techniques? How many people do we have to cram into a room in order to guarantee that at least 2 people have the same birthday? So in this case, the days of the year would be the boxes. You'd have the number of days in a year, and then we would need to be careful and allow for leap year. So the maximum number of days that we can have in a year is 366. And really what we're saying is, how many people do we have to have in order so that when we distribute people into those days of the year, we're guaranteed that 2 people share the same day. And so what you notice is that you would need 367 people to guarantee definitively that you had 2 people sharing the same birthday. If you do probability, it turns out that to have 2 people had to have it be greater than a 50% chance for there to be 2 people in the room with the same birthday. You don't need nearly that many people, but to be 100% certain, you would need 367. How many words must there be in order to guarantee at least 2 words begin with the same letter? Well, if we go by the English alphabet, we have 26 letters in the English alphabet. So the pigeonhole principle would say, hey, you need at least 27 words to distribute to the 26 boxes. The boxes are the letters, to guarantee that 2 of the words must be starting with the same letter. Finally, how many students do you have to have in a class in order to guarantee that at least 2 students receive the same score? If scores are given from 0 to 100, rounded to the nearest whole number, so we're not allowing anything after the decimal place, no tenths, no hundredths, for example. So in this case, you would have to indicate how many scores are possible. What's the number of possible scores? And in this particular case, we want to recognize that we actually have 101 possible scores, because the numbers 1 through 100, that's 100 numbers, and 0 is actually the 101st number. So there's 101 possible scores. So we would need 102 students to guarantee definitively that two of them had the same score. Now, probabilistically, swallow that word. Probability would tell us that we would need far fewer than that, working with expected values and those types of things. But to guarantee definitively, we would need 102. So the generalized pigeonhole principle says, hey, if we have n objects and we're placing them into k boxes, then at least one box contains the ceiling function applied to n over k. So the idea here is you have n objects. So let's say we have 11 objects for a concrete example, and we're going to place them into k boxes. So let's say we have, for a concrete example, let's say that we have 3 boxes. So what the generalized pigeonhole principle says, hey, if you have 3 boxes and you're going to distribute things into the 3 boxes, there's lots of ways that you could do it. So for example, I could go all crazy and put 11 objects in box number 1. I could just put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We could put all 11 objects into one box. That would be one possibility. But if you wanted to kind of ensure that you put the fewest number of items into each box, that was possible. What you would need to do is evenly distribute the elements into the boxes. So if I took 11 objects and I evenly distribute them into 3 boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that would kind of minimize the number of elements in each box by doing an even distribution. And what the generalized pigeonhole principle is saying, hey, if you have 11 objects and you divide it by the number of boxes, 3, that you're distributing them into, so this is going to be, what, 11 thirds is what, 3 2/3? So that the ceiling function, maybe I should make sure everybody knows what the ceiling function is. The ceiling function, I think we've looked at it already, but it's the round up function. You always round up to the nearest integer value. So if we take 3 2/3, it would round up to a 4. You always round up to the nearest integer. So the generalized pigeonhole principle says, hey, you're going to have at least one box that has 4 elements in it. In this case, we actually get 2 of the 3 boxes that have 4 elements in it. And so a good question that you could ask yourself is, does this numerator tell you how many boxes would have the 4 elements in it if you were doing an even distribution? So we don't have to distribute things evenly, but if we did, is that 2 out of 3 telling us the number of boxes that we would have the 4 elements in? So something to think about. So the generalized pigeonhole principle, if we apply it to a few problems, we could say, hey, if you have a group of 100 people, how many were born in the same month? So we would be distributing the 100 people into the months. The months would be the boxes. The people are getting distributed. And with the pigeonhole principle, I think that's one of the challenges, is kind of determining what the boxes are versus the objects. That's kind of the key. It's not always easy to tell the difference between the objects and the boxes, but in this case the months would be boxes, the people would be the objects getting distributed. And so the generalized pigeonhole principle would say that, hey, if you distributed 100 people to 12 months to find out if there was boy, I just botched that, didn't I? We're determining how many people are guaranteed to have been born in one of the months. You know, we could distribute all 100. They could all be born in December, but that's not likely. So you're kind of putting, hey, there's at least one month with this number of people in it. It could be more. So we would take the ceiling function, apply it to 100 divided by 12, and it looks like this could be reduced down to 25 over 4 goes into 12 3 times. which is what, 8 times 3 is 24, would be 8 1/3. So the ceiling function would round up to a 9. So this would tell us there's at least 1 month with 9 people. Like I said, it could be 1 month has all of the 100 people, but we know one of the months must have 9. What is the minimum number of students required in a class in order to ensure that at least 6 will earn a grade or the same grade, given that the possible grades are A, B, C, D, F? So really what we're going to do here is distribute students to grades. So there's going to be 5 boxes. The grades are the boxes. We distribute students to the boxes. And what we want to find is what's the smallest n? What's the smallest n, or the smallest number of people such that n over 5 equals 6? Well, one thing that we can realize is that if we had 25 divided by 5, you would get the ceiling of 5, which is just itself. It just rounds to itself. He's the nearest integer. So you've got to have one more than 25. So I can get this by saying, hey, if I have 5 students, 5 times 5, if I want 5 students evenly distributed to 5 grades, I would need 25 students to evenly distribute those 25 students to 5 grades. So I'm going to need one more than that. I'm adding it already. I would need one more than that, which would be 26. So 26 would be the first number such that 26 over 5, which is going to be equal to 5 1/5. There's my numerator of 1. This is going to round up to a 6. So I would need 26 students to guarantee that at least 6 students have the same grade. The mistake that would be easy to make here would be to just take the 6 and multiply it by the 5 to get a 30, but that's a larger number than what we actually need. So I'm going to do this next example on the next slide. I think I moved it onto the next slide. So it says, what is the least number of area codes needed to guarantee that 25 million phone numbers have distinct 10-digit stop it already. Distinct 10-digit telephone numbers. So we get the pattern NXX, NXX, XXXX for our phone numbers. X represents the numbers 1 through 10, and N represents numbers 2 through 9. So X corresponds to 10 possibilities, N corresponds to 8 possibilities. And we want to know how many area codes we need in order to get distinct phone numbers for all 25 million phone numbers. So what you do is you say, hey, if I don't have an area code, if I just have the NXX, XXXX, if I don't have area codes, how many numbers can I generate? Well, this is going to be 8 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6, which is really just 8 million. It's an 8 with 6 zeros after it. This is 8 million. So we're going to distribute the 25 million phone numbers that we want into 8 million boxes. And we want to find out if we do an even distribution, how many numbers will get distributed into a single number here. So if I do 25 divided by 8, which is what, 3 1/8? This rounds up to 4. So what this 4 tells me is that from these 25 million phone numbers, there's going to be at least 4 numbers that match exactly with this NXXXXXX pattern. We've distributed the 25 million numbers into 8 million boxes. At least one of those boxes, and those boxes are numbers that look like this, at least one of those boxes will have 4 phone numbers. So to make those 4 phone numbers distinct, you would need 4 area codes. And that's the answer to the question. What is the least number of area codes needed to guarantee that these 25 million phone numbers are distinct? And this makes sense. If you've got 4 that are the same, at least 4 that are the same, then you need 4 area codes to prepend to those numbers to make them unique. So now we get into a more difficult application. I'm going to do 3 that are similar to this because these are a little bit more difficult. So hopefully by giving several examples, it'll help with the homework. So here we go. There are 11 girls, 9 boys in a class. If we assign a unique integer, meaning we can't repeat an integer, if we assign a unique integer from 1 to 20 to those boys and girls, we want to demonstrate or prove that at least 2 girls have consecutive integers. And if 2 integers are consecutive, so for example 4 and 5 are consecutive, we want to recognize that the difference between consecutive integers is 1. So this number is going to be important to me. So what I'm going to do is, for my 11 girls, I'm going to let n sub I represent the integer that got assigned to them. So n sub I is going to be a number between 1 and 20. It's going to correspond to the integer that was assigned to the ith girl. So we recognize then that I is going to be a number. I is going to be a number between 1 and 11 because there are 11 girls. So again, n sub I is going to be the integer between 1 and 20 that's assigned to the ith girl, where the girls are going to run 1 through 11. There's 1 through 11 girls. And then I'm going to take each n sub I, I'm going to add 1 to it. I'm going to add 1 because adjacency requires a number of 1 to be between 2 things. So this tells me that n sub I plus 1 is going to be a number between, well, the smallest n sub I can be is 1. So if I do n sub I plus 1, the smallest number n sub I plus 1 can be is 2. And the biggest is 20 plus 1 is 21. So n sub I is going to be a number between 2 and 21. And because I runs from 1 to 11, there's going to be 11 of these. There's going to be 11 n sub i's. And there's going to be 11 n sub I plus 1. So 11 plus 11 is 22. So I'm going to have 22 integers. 11 n sub i's. 11 numbers generated by doing n sub I plus 1. I'm going to have 22 integers. But the value of those integers is going to run from 1. 1 will be the smallest possible integer in that set of 22 integers. And 21 will be the largest possible integer in that set of 22 integers. And because there's more integers, then there are possible integer values. The integer values run from 1 to 21. I'm going to have 22 integers in the 2 sets. That's going to tell me that there must be an index for some ij, for some I and j, where the I and j represent the indices here. 2 of the numbers are going to have to be the same integer. There must be an I and a j such that a sub I equals a sub j plus 1. There has to be two integers that are the same between these two sets of things. There's going to be two that are identical. I know that because the n sub i's are each distinct. And I know the n sub I plus 1 is going to create distinct integers between 2 and 21. These are all distinct. And because there's 22 integers, and I know that two of them must be the same integer, and because integers within either set are distinct, it must be the case that something from here, which looks like an a sub I kind of thing, actually I should be using n's because that's what I chose to use. There's going to be some n sub I from this set that has to equal some n sub j plus 1 from the other set. And then if I subtract n sub I minus n sub j, if I subtract n sub j from both sides, I see that the difference between the two numbers is 1. And if the difference between two numbers is 1, that means those two numbers are adjacent to each other. So that means there must be two girls who have been assigned consecutive integers. Why? Because the n sub i's represent what? They represent the integer that was given to the girl. So if this girl was given the integer n sub j minus this girl, or sorry, n sub I, and this girl was given integer n sub j, and the difference between those two integers is 1, the girls have been assigned consecutive integers. So another problem just like it, different context but same principle. Suppose we have an incomplete deck that has 26 black cards and 19 red cards, and we shuffle those cards all together. We show that there must be two black cards that are exactly 6 cards apart from each other in the deck. So I'm going to let b sub I represent the position of the ith black card in the deck. So how many cards are in the deck? There's 26 plus 19 cards altogether in the deck. So there's going to be 45 positions. 45 positions that are possible to be in that deck of 45 cards. So that tells me that b sub I has to be a number between 1 and 45, and I has to be a number between 1 and 26, because it's the ith black card. There's 26 black cards. The ith black card will be in position b sub I. So the b sub i's are going to run 1 through 45. I runs 1 through 46. And I want to think about what does it mean to be 6 cards apart. Well, we would need the difference between two position numbers to be 6. So I'm going to take the b sub I, the position number, and I'm going to say, hey, what does b sub I plus 6 look like? Well, b sub I plus 6 is going to be a number between the smallest b sub I, the position number b sub I can be is 1, so 1 plus 6 is 7. And b sub I plus 6, the biggest it could be is 45 plus 6, which is 51. That's the biggest b sub I plus 6 could be. So how many b sub i's are there? Well, I goes from 1 to 26, so there's 26 b sub i's. And how many b sub I plus 6 numbers are there? Well, there's going to be 26 of them here. And I know that these b sub i's are distinct. No two of them are the same. That's the key. No two are the same, which means that b sub I plus 6, each of those will be distinct or unique. There won't be any two numbers. There's 26 b sub I plus 6's. No two of them can be equal to each other. Because b sub I is a position in the deck, no two cards can share the same position. So we have two distinct sets of integers. Altogether, there's 26 of these, 26 of these, which means there are 52 integers that get generated, 52 integers. And the values of those integers are going to range from 1 as the smallest all the way up to 51 will be the largest value. And because there are 52 integers, and they only are going to range from 1 to 51, so those are 51 boxes. These 52 integers distribute into 51 boxes. That tells me that one of the b sub i's, there's going to be indices I and j exist such that one of the b sub i's from here is going to equal a b sub j plus 6. If I subtract b sub j from both sides, I get b sub I minus b sub j equals 6. And if I subtract b sub I minus b sub j, this position minus this position in the deck, if the difference between those two positions is 6, that means these two cards, the ith card and the jth card, are 6 units apart from each other, which is what we were trying to show. So, last example, it's exactly like the other two. Again, a different context, identical principle. So here we have a traveler. The traveler is visiting 24 towns. And my pin's being wonkus again. There we go. The traveler is going to visit 24 towns in 15 days. If the traveler visits at least one town each day, show that there must have been, so at least one town each day, there must have been some period of consecutive days during which he or she visited exactly 5 towns. So this at least one town each day is going to be important. I'm going to try to remember to say why it's important. It's easy for me to kind of gloss over the importance of this claim right here. But so here's the idea. I'm going to let v sub I represent the number of towns visited by day number I. All right, so v sub I, that means that v sub I is going to be a running total. Each time I visit a town, that day I change v sub I to represent the total number of towns I visited up to that point. So we keep a running total. And this claim that we have to visit at least one town each day, that tells me that there is no I and j such that v sub I will equal v sub j. So this is important because it tells us that these numbers are distinct or unique. So v sub I, if it's the number of towns I visited, the total number of towns I visited up to that point on the ith day, then v sub I is going to have to be a number that runs between 1 and 24, because I'm going to visit a total of 24 towns. And v sub I is going to be my running total, keeping track of how many towns I visited up to the ith day of my travels. So because I represents the days traveled, I is going to be a number that runs from 1 to 15. 15 days is my travel period. And then I want to identify that there was a period of some consecutive days during which I visit exactly 5 towns. So if I visit exactly 5 towns between days I and j, I need v sub I minus v sub j to equal 5. The change in number of towns visited to equal 5 to show that exactly 5 have been visited over that range of days. So what I'm going to do is explore v sub I plus 5. What does it mean to add 5 so that the change in towns visited is 5? Well, v sub I plus 5 is going to be a number that runs from 5 plus 1 is 6 up through 5 plus 24 is 29. And we want to remember that these are distinct numbers here. The v sub i's are distinct, so no two are the same. And if no two of the v sub i's are the same, then v sub I plus 5 will also be a set of 15 distinct integers. We know there's 15 of them because the I represents the ith day of travel, and there's 15 days of travel, so there'll be 15 distinct v sub i's. There will be 15 distinct v sub I plus 5's. So if there's 15 numbers in each set, there's 30 integers altogether. And those integer values are going to run from 1 to 29. And the moment we know that, we know we have more integers than there are possible integer values, tells us one of the integers in this set was going to equal the value of an integer in this set. So there must exist an I and a j such that, an I and a j, such that v sub I is going to equal v sub j plus 5, which means if I subtract the v sub j from both sides, means that the difference between v sub I and v sub j is 5. So there must have been a period of days during which exactly 5 towns have been visited. So we'll shift gears and do a geometry application of the pigeonhole principle. So suppose there are 10 farmers. They're on a square plot of land that is 3 miles long per side. Show that there must be 2 farmers within square root of 2 miles of each other. So I've got a square plot of land. Hello, square plot of land. I've always wanted to draw you. And I'm going to break this up into 1 mile chunks. So I'm going to break it into 1 mile squares. And then what I'm going to do is take my 10 farmers, have my 3 mile by 3 mile chunk broken into 1 by 1 squares. Well, these are 1 by 1 squares. I'm going to take my 10 farmers and I'm going to say, hey, the farmers have to be, I'm going to distribute the 10 farmers onto the 3 by 3 plot of land. So farmer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's more farmers than there are 1 by 1 chunks of land. So that tells me that there must be a 1 by 1 square that shares 2 farmers. And if there's a 1 by 1 square that shares 2 farmers, what's the furthest apart they can be? Well, putting them on the diagonals of on the vertices of the square would get them as far apart as they can possibly be from each other on that plot. And these are 1 by 1 squares in here. So the Pythagorean theorem would indicate that this distance is square root of 2. So the farthest possible distance that they can get apart from each other is the square root of 2 miles. All right, final example for pigeonhole principle. So this example says, given any 5 points on a sphere, show that there must be a closed hemisphere that contains at least 4 of the points. So a closed hemisphere means pass a plane through the center of the sphere so that the sphere is cut exactly in half. And then we want to show that there has to be at least 4 points on a closed hemisphere. And when we say closed, what we mean by closed, let's say I have the Earth as my sphere, and I put the equator around the Earth. And the equator, the plane of the equator, breaks us into an upper and lower hemisphere. And by closed hemisphere, I mean that I need to include the boundary or the equator as part of the hemisphere. So that's all closed means. It means you don't get to ignore the boundary. 2 points on the boundary that break the sphere into 2 hemispheres, those are included in the 2 hemispheres. You include the boundary as part of each hemisphere. So the way that you could run this argument is you could say, hey, suppose I have a sphere, pretend this is a sphere, not a circle, and it has a center, and now take 5 points, distribute any 2 of them, it doesn't matter which 2 you pick, distribute any 2 of them onto the sphere. The moment that you do that, the 2 points on the sphere plus the center of the sphere form a plane takes just like it takes 2 points, 2 distinct points to form a line, you need 3 distinct non-collinear points to form a plane. So the moment you have these 3 points, and they are distinct and non-collinear, because the guy at the center of the Earth is going to be this. It's not going to lie in the same. It's not going to lie on the same curve that the 2 points on the surface do. So you construct the plane formed by those points, and you use it to break it into an upper, and lower hemisphere. And now you distribute the other 3 points. We started with 5 points. We distributed 2 onto the surface. Now we have 3 points left. And where can we distribute them? Well, if we distribute them onto the same plane or line that these 3 points form, then there will definitely be a closed hemisphere that contains at least 4 points. And then we could say, well, what if we don't put them on that same line? Well, then I would have to distribute them either into the lower or upper hemisphere. So if I do an even distribution of the 3 points that are left, 1, 2, 3, an even distribution, now I have 4 points lying in the same closed hemisphere. I have the 2 points that I used to form the hemisphere, plus the 2 points distributed onto the hemisphere. So this demonstrates that there are at least 4 points on any closed hemisphere given a set of 5 points.